The process begins with rolling, where high-quality steel is selected and processed into sheets or coils of the desired thickness. This step is crucial, as the steel's composition and uniformity influence the saw blade's performance and longevity. The rolled steel is then flattened and prepared for further processing. Once the steel sheets are ready, the next step is laser cutting. A high-precision laser cutter is used to cut out circular saw blades of different sizes and shapes. This technique ensures minimal material waste and allows for precise cuts, which are essential for the saw's performance. Additionally, laser cutting helps maintain uniformity across batches, ensuring each blade meets the required specifications. The process begins by securing the steel sheet onto the cutting platform. A focused laser beam, controlled by computer numerical control (CNC) technology, follows a predefined pattern to cut the blade precisely. The high-energy beam melts or vaporizes the metal along the designated path, resulting in a clean and burr-free cut. To prevent thermal distortion, a cooling system, often using gas jets such as nitrogen or oxygen, is employed to regulate the temperature. This method allows for the creation of intricate blade designs, including venting holes for heat dissipation and noise reduction. The precision of laser cutting ensures consistency, making it easier to balance the blade during later machining stages. After the blades are cut, they undergo heat treatment to enhance their hardness and durability. This process involves heating the blades to high temperatures and then cooling them rapidly. The controlled heating and cooling cycle improve the steel's strength, making it more resistant to wear and deformation. Heat treatment is critical for ensuring the blade retains its sharp edge over extended use. Milling is the next step, where the saw blade's surface is machined to refine its shape and dimensions. This process removes any rough edges or inconsistencies left after laser cutting and heat treatment. Precision milling helps maintain the blade's balance and ensures it runs smoothly when mounted on a saw machine. Following milling, the blades undergo grinding and polishing. Grinding is essential for achieving a smooth and uniform surface, which reduces friction and improves cutting performance. Different grinding techniques, including flat and hollow grinding, may be used depending on the saw blade's intended application. After grinding, polishing is performed to enhance the blade's appearance and reduce surface imperfections. To prevent corrosion and oxidation, the blades are coated with a thin layer of protective oil. This step also helps in preserving the blade's finish before it reaches the customer. Additionally, demagnetization is carried out to eliminate any residual magnetic fields that might interfere with the blade's operation. Before proceeding to further steps, a thorough check of the bore, center hole, is conducted. The bore is crucial as it determines how the blade will fit onto the saw machine. After the bore check, the blades undergo a washing process to remove any oil residues, metal particles, or contaminants. This step ensures the blades are clean and ready for the next stage of the manufacturing process. Clean blades improve bonding during later stages, such as brazing. Brazing is the process of attaching carbide or diamond-tipped cutting teeth to the steel blade. This is a crucial step as it enhances the cutting performance and longevity of the blade. During brazing, the cutting tips are precisely positioned and bonded to the blade using a high-temperature soldering technique. The bonding material ensures a strong connection, allowing the teeth to withstand high-speed operations without detaching. The final step in the process is sandblasting, which involves blasting the blade with fine abrasive particles to remove any remaining impurities and create a uniform surface finish. Sandblasting enhances the blade's aesthetics and improves its resistance to wear and tear. It also helps in creating a slightly roughened surface that can reduce friction and improve cutting efficiency. The manufacturing process of a circular saw is a journey involving multiple precise and controlled steps. Each stage plays a crucial role in ensuring the blade's durability, sharpness, and efficiency. From rolling and laser cutting to brazing and sandblasting, each step contributes to the final product that is ready to tackle a variety of cutting tasks in different industries. With the combination of advanced technology and quality control, the birth of a circular saw ensures high performance and long-lasting reliability. To measure the height of the bearing outer ring using a micrometer, first clean the surface to remove dust or debris. Position the micrometer accurately on the bearing's outer ring and apply gentle, consistent pressure. Use a standard block to calibrate the micrometer. Take multiple readings from different points to ensure accuracy and minimize measurement errors. The instrument, typically a micrometer or height gauge, is used to measure the height error of the bearing outer ring by comparing actual measurements with specified tolerances. A standard block is required for calibration to ensure precise readings. By placing the bearing on a flat surface and measuring multiple points, height variations can be detected, ensuring manufacturing accuracy and proper performance. To minimize measurement errors, take readings at multiple points around the bearing's outer ring. This helps detect irregularities, ensures consistent results, and improves accuracy by averaging out any deviations or inconsistencies. Marks are placed on the bearing components to ensure correct alignment during installation, preventing misplacement and ensuring optimal performance and longevity. To measure the length of the bearing outer ring, use a precision measuring tool, like a caliper or micrometer. Ensure the ring is placed on a flat surface and take multiple measurements for accuracy. Measure the inner ring length using a caliper for precision. Longmore's ARB electric resistance welding manufacturing process. Longmore is a globally recognized producer of electric resistance welded ARB pipes, meeting the stringent requirements of leading oil and gas companies. The edge milling unit precisely trims and machines pipe edges to close tolerances, ensuring optimal weld preparation and uniform seam integrity. Round forming is a critical stage in Longmore's ARB manufacturing process, where flat steel strips are gradually shaped into a cylindrical form. This is achieved using an advanced continuous forming system that applies precise mechanical pressure to bend the steel into a perfect round shape without compromising its structural integrity. The process ensures consistent geometry, which is essential for high-strength applications in the oil and gas industry. By maintaining tight dimensional tolerances, round forming minimizes stress points and defects, providing a seamless transition to the welding phase. This precision guarantees uniformity, reducing the risk of inconsistencies in high-grade steel pipes. The hydrostatic test subjects pipes to high-pressure water up to 300 bar to verify strength, leak resistance, and structural integrity. Forging is the first step in manufacturing large spherical roller bearings. High-quality alloy steel is heated to 1,100 to 1,250 degrees Celsius and shaped using hydraulic presses or hammers. The inner and outer rings are hot forged into near final dimensions, enhancing grain structure and mechanical strength. Turning involves CNC lathes machining forged rings to precise dimensions, ensuring correct diameters, smooth surfaces, and proper geometry for further processing. CNC machines drill precise holes in cages for roller placement. Rollers are cut to size with tight tolerances for uniformity. Rollers are hardened and tempered for strength, durability, and wear resistance. Rings undergo case hardening or through hardening followed by tempering to enhance wear resistance, toughness, and load-bearing capacity while minimizing distortion. Grinding ensures precise dimensions, smooth surfaces, and correct profiles for rings and rollers. Quality control includes dimensional checks, hardness testing, and surface inspections. During assembly, rollers, cage, and rings are carefully fitted together, ensuring proper alignment and clearance. Lubrication is applied, and the bearing is tested for smooth rotation, ensuring durability and optimal performance under heavy loads. Bearings are coated with anti-corrosion oil, wrapped in protective materials, and packed in sturdy crates to prevent damage during storage and transport. Mounting large spherical roller bearings requires precision to prevent damage and ensure longevity. The bearing seat and shaft must be thoroughly cleaned before installation. For a tight fit, the inner ring is heated to 80 to 120 degrees Celsius using an induction heater or oil bath, allowing it to expand for easy mounting. After cooling, it securely grips the shaft. Proper lubrication is applied, and housing alignment is checked. Final inspections include clearance measurements and smooth rotation testing, ensuring optimal performance under heavy loads. Measuring the outer ring involves precise dimensional checks using high-accuracy instruments to ensure tolerance, roundness, and surface quality for assembly. Measuring the inner ring ensures accurate bore diameter, roundness, and surface finish using precision gauges to meet strict tolerance and performance standards. Selection of balls involves measuring diameter, roundness, and surface finish to ensure uniformity, durability, and proper load distribution within the bearing assembly. Joining the rings involves aligning the inner and outer rings precisely, ensuring correct clearance and fit to facilitate smooth rotation and durability. Fitting the balls involves placing precision-selected balls between the inner and outer rings, ensuring uniform spacing for smooth rotation and load distribution. Spacing of the balls ensures even distribution within the bearing, preventing contact between them and optimizing performance, reducing friction, and enhancing durability. Fitting the cage involves securing it around the balls to maintain proper spacing, reduce friction, and ensure smooth, efficient bearing operation under load. Cage riveting secures the cage in place, ensuring stability, proper ball retention, and smooth rotation while preventing displacement during bearing operation. The manufacturing process of bearings at ARB Bearings is a highly sophisticated and quality-driven procedure. ARB Bearings, established in 1990 and headquartered in New Delhi, India, follows advanced manufacturing techniques to produce high-quality bearings that cater to various industries, including automobiles, industrial machinery, and household appliances. The process begins with the selection of high-quality raw materials. These materials undergo precision machining using fully automatic CNC grinding and super finishing lines. CNC-controlled turning processes ensure a high level of quality and accuracy in the production of bearing components. Heat treatment is a critical stage in manufacturing, where bearings are subjected to computerized and atmosphere-controlled processes to enhance their durability and performance. The bearings then undergo advanced washing procedures to ensure a standard and stable quality in every manufactured piece. During the assembly process, ARB Bearings follows a strict no-error policy. Each bearing is marked with a unique identification code, ensuring complete traceability. To prevent counterfeiting, packaging includes special anti-counterfeit protection measures. Quality control is an integral part of the manufacturing process. ARB Bearings employs stringent quality checks at all stages of production. This includes testing for vibration, noise, endurance, and overall performance to ensure that every bearing meets international quality standards. The company's quality management system is accredited with ISO TS 16949-2009, OHSAS 18001, and ISO 14000 certifications. ARB Bearings also emphasizes innovation, with an in-house research and development team dedicated to creating new and improved bearing designs. The manufacturing process begins in the yard department, where inbound scrap material is received from local vendors. The scrap material primarily consists of shredded automotive scrap, steel plates, structural material, automotive motors, and heavy automotive bundles. Additionally, some returns are generated in-house. The scrap is unloaded from trucks into designated areas, and then transported by cranes into railcars. A locomotive moves the railcars to the charge area, where the scrap is prepared for melting. The scrap metal is melted in a cupola furnace, where it is subjected to intense heat produced by burning coke as fuel. To aid the process, limestone is added to help remove impurities and keep the molten metal fluid. Silicon is also introduced to enhance the metallurgical properties of the iron. As the metal melts, it flows out of the tap hole into runners that direct it into ladles. At this stage, the molten iron undergoes desulfurization, where calcium carbide is added to reduce the sulfur content. An operator skims off slag and spent carbide to ensure the molten iron is clean. Samples are taken for metallurgical analysis to verify the composition and quality of the metal before proceeding to the next step. The pipes undergo thorough quality control inspections to check for defects such as cracks, irregularities, or weak spots. Special emphasis is placed on ductility testing to ensure the pipes meet industry standards for flexibility and strength. Any defective pipes are identified and removed from the production line. To enhance durability and resistance to internal abrasion, the inside diameter of the pipe is coated with cement lining. This process involves inserting a lance into the pipe to inject cement, after which the pipe is spun at high speed to ensure an even coating. The lined pipes then pass through a walking beam conveyor to the curing tunnel, where the cement lining is dried and hardened. Once the cement lining process is complete, the pipes move to the painting section for external coating. A paint machine applies a protective layer to the outer surface of the pipe, which acts as a barrier against environmental corrosion. The external coating resembles a silky finish inside and a textured finish outside, similar to house paint. At this stage, inspectors ensure that each pipe has received the proper amount of paint. They also verify that there are no defects in the coating. Once approved, a quality checker stamps each pipe with information regarding its weight, length, and specifications. Water systems are essential infrastructure, ensuring reliable supply for drinking, firefighting, and sanitation during disasters. Wildfires have increased in size, duration, and intensity beyond historical norms due to climate change, prolonged droughts, and higher temperatures, causing more frequent and severe impacts on communities, ecosystems, and critical infrastructure. Clean, safe water is essential for survival, recovery, and public health. U.S. Pipe produces resilient ductile iron pipes by melting recycled scrap metal at 2,700 degrees Fahrenheit for strength. Most wildfires reach average temperatures of 1,400 degrees Fahrenheit, with extreme cases nearing 2,000 degrees Fahrenheit, generating intense heat capable of destroying vegetation, structures, and infrastructure, while severely impacting water systems and firefighting efforts. U.S. Pipe conducted a controlled study to measure our ductile iron pipes' performance in a wildfire scenario. Experiment based on ISO 19921 industry standard for maritime piping systems. The pipe endured 45 minutes in a 1,500 degrees Fahrenheit fire, proving its durability and resilience. After exposure to a 1,500 degrees Fahrenheit fire for 45 minutes, the ductile iron pipe was pressure tested at 500 psi for 10 minutes to evaluate its structural integrity. The test confirmed 0 leaks, demonstrating the pipe's ability to withstand extreme conditions while maintaining a secure, sealed joint, ensuring reliable water delivery even after a wildfire event.